We conclude our discussion of graphs with an example that draws a graph and allows the user to perform both types of graph searches, determine whether the graph is connected or has cycles, and to display its connected components. There are two aspects of this program that require some additional explanation. The first is our approach to drawing a graph, and the second is the implementation of the disjoint union data structure that is needed to determine the connected components. We begin with our approach to drawing graphs. Drawing arbitrary graphs is a challenging problem if we want the graph to look attractive and to minimize crossing edges. So our approach will be a simpler one, in which the client specifies the location of each vertex. With that approach, we need an interface that defines the XY coordinates and the name of the vertex. We named this interface displayable. It requires three methods: one to get the X ordinate, one to get the Y ordinate, and a third to get the name of the vertex. In our application, the class that will draw the graph is the Graph View class. As with all drawing classes, it extends the JPanel class. It will have one instance variable, which is the graph itself, which will be supplied by the constructor, which we have omitted. Note that the type of the graph is constrained by using an upper bounded wildcard, which means the vertex type is a type that implements displayable. Overriding the paint component method is always what is needed to do the actual drawing. We need a list of vertices to accomplish this task. Note again, the type of the list uses an upper bounded wildcard. Then it loops through all the vertices, gets the XY coordinates of the vertex and the vertex name, draws a solid circle to represent the vertex, and displays the vertex name above it. A second similar loop is needed to draw the edges. Next, we consider the disjoint union data structure. It is also sometimes called a dynamic equivalence relation. The reason is that its components can be thought of as equivalence classes that partition the whole set. It has two fundamental operations: the union operation that takes two equivalence classes and forms their union and turns them into one class, and the find operation that, given an element, returns the equivalence class it belongs to. We will use it to determine the connected components of the graph. The way it is done is by performing a graph search and taking the union between every pair of connected vertices. Initially, all vertices will belong to separate equivalence classes, and as the search proceeds, they will join the equivalence class of all vertices they are connected to. Now let's look at how the two main operations of a disjoint union would be implemented. As the representation, we use the built-in Java map class and instantiate it with a generic element that is mapped to a set of those elements. In our usage, the elements will be the vertices of the graph. The union method accepts two elements and returns whether the operation succeeds. It fails if either element is not in the map. Otherwise, it uses the get method of the map to get the equivalence classes that correspond to each element. The union of the two classes is formed, and all the elements of that new equivalence class are mapped to it. And true is returned to indicate success. The find method is much simpler. It is given an element and it returns its equivalence class. That is accomplished by again using the get method of the map. Let's look at the structure of our graph example. The vertex class implements the displayable interface so that this graph can be drawn. The rectangular graph class is a subclass of graph. It uses the disjoint union to create the connected components. And the graph GUI class defines the GUI that provides the interface. It contains an instance variable of the graph view class to allow the graph to be drawn. So now let's run it on a few different graphs. And this is set up so that we can load some predefined graphs. So in the first case, let's do the depth first search. And what we notice at the bottom is it enumerates the vertices beginning with vertex A in depth first order. Breadth first will look different from that. We'll check whether the graph is connected, and we should expect the answer to be that it is, which it tells us. And check whether it has cycles. It has no cycles, and it indicates that. And because it's connected, it should only have one connected component, which it does. All right, let's do one more. With the second graph, we'll skip the searches again and check connectedness. In this particular case, the graph's not connected, so it should tell us that. It still has no cycles. And now when we look at the connected components, it should show us two sets of connected components, because the graph is not a connected one like the previous one was. You can try it on some other examples to see how some of these other operations work.